University of Toronto, with a cross appointment at the Department of Mechanical and Industrial Engineering. His research interests are in reinforcement learning and machine learning, with a focus on developing empirically sound algorithms for challenging industrial problems. He received his PhD from the University of Alberta in 2011, followed by the postdoctoral fellowship at McGill University from 2011 to 2014, and CMU at 2014. Prior to joining the Vector Institute in 2018, he worked as a principal research scientist at Mitsubishi Electric Research Laboratory in Cambridge, US for 2 years. Okay, now we are ready to listen to his presentation, which is about the approximate dynamic programming and batch reinforcement learning. Thank you very much.
سلام، امیر-مسعود فرهمند هستم و پژوهشگری در مؤسسه وکتور در تورنتو کانادا و همچنین استاد دانشگاه در دانشگاه تورنتو دپارتمان کامپیوتر ساینس. خیلی خوشحالم که این موقعیت پیش اومد که امروز میتونم با شما صحبت بکنم و حداقل از راه دور و راجع به این در واقع موضوع Approximate Dynamic Programming و Batch Reinforcement Learning صحبت بکنم. من فقط یه مقدمه‌ای بگم که شاید جالب باشه که من سالهای پیش در IPM پژوهشگر بودم وقتی دانشجوی کارشناسی ارشد بودم و با دکتر در دانشگاه تهران با دکتر نیلی و عرابی و لوکس کار میکردم. یه فکر کنم حدود 2 سالی در IPM کار میکردم. چون ازم خواسته شده که به انگلیسی صحبت بکنم، درنچه سویچ میکنم به انگلیسی و بقیه سخنرانی و در واقع سخنرانی رو به انگلیسی ارائه میدم. Okay, so I'm going to talk about approximate dynamic programming and batch reinforcement learning. It will become more clear what batch reinforcement learning and approximate dynamic programming are. But basically, batch reinforcement learning, for those of you who know something about reinforcement learning, is a reinforcement learning where the agent cannot interact with the environment. So there's a batch of data, a bunch of data points that you have already collected, and now you want to learn a good policy out of them. And the reason that we focus on batch reinforcement learning, there are 2 reasons. One reason is that, well, in some safety critical tasks, we cannot let agents to interact with the environment, but we have a lot of data that has been collected in some way, and we still want to learn a good policy out of it. And the other reason is that by studying batch reinforcement learning, it makes the problem of analyzing reinforcement learning a little bit easier, because we do not need to be worried much about how the agent should explore. The data has already been collected, and now we can focus on what kind of performance guarantees we might have given this amount of data. So I'm going to talk about first a brief introduction to reinforcement learning. I'm sure many of you already know about it, so I go through them fast. And then I am going to talk about some approaches to solve reinforcement learning problem and dynamic programming problems, and then gradually move on to the situation that we call batch reinforcement learning. And at the end, I'm going to talk a little bit about the type of analysis and type of guarantees that we might have about reinforcement learning, specifically batch reinforcement learning. Okay, so there are different methods for solving reinforcement learning problems. One way to categorize them is categorizing them based on whether they're value-based methods or policy search type of methods. So value-based methods, there are kind of one famous example is something like Q-learning. The basis of them is based on the principle of dynamic programming. That's for when we have that basically describes how the value at one state is related to the value of other states. And we can define dynamic programming through it. But the problem is that if you have a large state space or action space, then we cannot do dynamic programming exactly, so we need to do approximate dynamic programming. And that's why I'm going to talk about approximate dynamic programming, because this can be seen as a good step towards understanding how reinforcement learning should be done when we have a large state space. The other type of problems or methods would be a policy search type of method. A famous one is kind of an algorithm such as reinforce. It's a policy gradient type of method. And of course, there's a lot of overlap between these two methods. So there are methods that both benefits from value function, but also use that value function to guide the search in the policy space. So methods like actual critique belongs in this intersection. Here I'm going to talk about focus on value-based type of methods. So what is reinforcement learning? Reinforcement learning at very high level is a problem that we have an agent. It can be a robot, it can be a air conditioning system, doesn't really matter. It observes the environment, the world, through some sensors, maybe for a robot it would be cameras or other sensors. For an air conditioning system, it might be sensors that measures the temperature. And based on that measurement, the agent takes some action, and as a result, its state changes. So the robot moves, for example. And why does it do all these things? Because it has a goal of achieving some kind of long-term rewards. So it wants to kind of maximize these long-term rewards, and this basically defines the reinforcement learning problem. So we can say that reinforcement learning problem is the problem that we have an agent that continually interacts with the environment, and now we should figure out how it should choose its actions so that its long-term rewards are maximized. People in different communities, for example, in control engineering, control theory, might call this the problem of adaptive controller or stochastic nonlinear dynamical systems, or maybe some other people more from AI background, like outside reinforcement learning, they might call it the problem of designing an adaptive situated agent. But these are all very similar, but with some critical differences, of course, that I'm not going to talk about. So my focus would be mostly on reinforcement learning, as we know it in computer science and in the machine learning community. So let's talk about reinforcement learning agent. What is reinforcement learning agent? Reinforcement learning agent is this kind of abstract concept. In practice, can be a robot, can be an air conditioning system, can be a car, or whatever. It observes some state x at time t, so I use x of t to denote state that it observes from the environment. And then it selects some action, a of t, following something called policy. So a of t comes from pi, which is a function of x of t. So, and then this action goes to the environment. And as a result, the state of the environment, the state of the agent in the environment changes. So we get x of t plus 1 at the next time step would be coming from a distribution that depends on x at time t and action at time t. So this P, this is transition dynamics, essentially encodes the dynamics of these environments or agent in the environments. Also, the agent receives some reward, R of t, which is again a function or distribution that depends on x of t and a of t, and sometimes it can also depend on the x of t plus 1. It doesn't change much. And then the agent repeats this kind of decision-making, selects another action at time t plus 1, and so on and so forth. So it is common to formulate this interaction of the agent with the environment within the mathematical framework of Markov decision processes, or MDP. And there are different ways to characterize it, but one type of MDPs are called discounted finite action MDPs, and it is basically defined by a set of X state, action states, so X as a state space, A as an action space, P as a transition probability kernel, R as an immediate reward distribution, and gamma, which is a discount factor. So I just want to mention that discounted finite, so here I'm going to focus on problems that have a general state space. I'm going to talk about what state space actually means, but has finite number of actions, and also it is discounted. So this discount factor, which I'm going to give a little bit more intuition about it later, is in some number between 0 and 1, smaller than 1. So this makes the problem discounted MDP. But then there are problems or mathematical formulations that is not, say, discounted. So I can think of it gamma being equal to 1. But I'm not going to talk about them, but just want to mention that those mathematical frameworks also exist. So let's try to understand this a little bit better. So what is state? State is essentially a variable that defines, kind of summarize the state of the agent in the environment. So for example, for a robot, it might be a variable that describes its position in the environment plus some internal variables that describes maybe the level of battery of the robot, or many other variables that describes, completely describes how, what has happened to the agent until this time. So here the agent might, at time t, might be one of the 6 states here. In general, we don't talk about a finite number of states. We talk about maybe a very large state space. Maybe it's described by a real valued vector. But here, for simplicity, I show just a finite number of states. And then what happens? The agent chooses one action, say action 1, and then with some probability goes to another state at time t plus 1. So this is probability of agent at x prime next time step being at state 2, condition on when the agent starts at state 3 and chooses action 1. So this has some probability. And it has going to state 3 or state 4 and so on, also has some other probabilities. So the agent also receives a reward when we move from one state to another. So which depends on the state that started and also the action that it takes. So here I'm showing you, so in the previous figure, this one I showed what happens if the agent is at state 3. We can say, talk about these probabilities from each of these states to any other states in the next time step. And these time steps can be expanded for multiple steps. And the agent, depending on the actions that it chooses, it follows some specific path. So it starts from state 3, for example, goes to state 2, state 3 again, state 4. And as I mentioned, it also receives some reward. So we can summarize the path that agent goes through state space by this sequence of, say, x0, x1, x2, x3 that depends on the action that is taken by the agent. And also, as I mentioned, the agent receives some reward, like reward 0, reward 1, reward 2, and reward 3, and so on and so forth, to measure the kind of the long-term performance of the agent, long-term reward of the agent. We have this notion of return, which is essentially summation of the rewards that the agent would receive. So here you see this is a weighted summation from time 0 to infinity. It's weighted by gamma to the power of t. If you recall, gamma was the discount factor, a number between 0 and 1. And this quantity, this return, basically defines how the agent has performed. If it is a higher value, the agent has performed better. So one thing that is important to notice, and probably you know already, is that if the environment is stochastic, so it is not deterministic, so when you choose some action, there is a good probability, there is some chance that you go to state 2, there is also some chance that you go to another state, state 3, then in that case, your return would be a random variable. It wouldn't be a deterministic function of your actions. So it fluctuates in some sense. In order to talk about performance of such an agent, one way to think about it is that say how much the agent performs in average if the agent starts from some particular state and follows some policy. So this is the notion of value function, which essentially says that if the agent starts from some state X, like state 3, at time step 0, and then follows a particular policy, this is the return that it would get, this summation. It has some fluctuation, but if we take the expectation of it, it wouldn't be a random variable anymore. And that would be the criteria that we use in order to quantify how well that agent that is following policy pi is performing at state, say, X. So this quantity is called value function. And also we have something called action value function, which is very similar with the difference that at the first step, the agent is starting at state X, but instead of choosing action from policy pi, it chooses action A, and then goes to the second time step. And then afterwards, it chooses, it follows actions according to policy. So the first step is not following a policy. Okay, so we have defined value function for policy pi and action value function for policy pi. So what is the goal here? As I already mentioned, the goal is for the agent to maximize its long-term performance or long-term reward. So we define the reward or some measure or some quantity that measures long-term reward. So that is the value function. And so we want to find the best value function, which is called optimal value function, which is essentially we search in the space of all possible policies and find a value function or action value function that maximizes it. And that is called optimal value function, and it's usually denoted by Q star or V star for state value function. So it can be shown that if you have the optimal value function, that gives you also the optimal policy. You simply need to choose at each state, choose the action that maximizes that action value function. So when you're at state X, if you know Q star, you choose action that maximizes it, and that would be your optimal policy, pi star. And the goal of reinforcement learning agent is then to find a policy that is close to optimal. So we find a Q pi star that's kind of close, or Q of pi that is close to Q star. So here, this is a typo. Q star is of course equal to Q star. What I mean is that Q of pi should be approximately close to Q star. Okay, so now that we have defined MDPs, the question is that how we should define an MDP and reinforcement learning problem. So I'm going to talk about value-based methods and specifically talk about dynamic programming approaches. So in order to describe dynamic programming, we need to talk about Bellman equation. So what is a Bellman equation? Bellman equation is an equation that describes an important relation between the value functions. So let's go through it. I just write the definition of the value function, action value function. Q of pi is the expectation of this reward, summation of rewards, weighted by gamma to the power of t when the agent starts at state X and chooses the first action according to action equal to A. So we just decompose this summation to the first step reward, R of X0 and A0, plus gamma times summation of gamma to the power of t of R t plus 1. So notice that here is R t plus 1. Here we have RT. So essentially, This is the summation starting from counting the rewards that we get from time equal to 1, 2, 3, and so on. So we notice that this is very similar, this quantity. This summation is very similar to the definition of the value function, with the difference that instead of starting from time step t or time step 0, here we start from time step 1. So this basically means that we can replace this expectation with its action value function, but not for the state that is x1, and for the policy that is pi of, or for the action that is pi of x1. Because from the second time step on, we choose actions according to policy. So essentially what we have is that we can write q of pi as expectation or reward at the first time step plus gamma times q at the next state. Or also we can write the expectation in the form of integral or summation, and this is this can be written in this form of r of small letter r of x and a, and small letter r is essentially the expectation of the reward that we get at the first time step plus gamma times integral of a q function, q of pi at next state x prime, with the action that is selected according to pi of x prime, and it's averaged according to the distribution of p of x prime condition x and a. So recall that this is the distribution that if we start at state x and choose action a, this would be the distribution of the next state. So here I'm showing you also it's kind of more visual form. So this is state. So we are saying that the value function here is equal to the reward that we get at the first step plus gamma times the average value that we get in these orange circles. And the average is weighted according to probability of going to those states. So this quantity, so this relationship, this equation is called Bellman equation. And it's very important because it says that how the value at one state is related to the value of other states at the next time step. And also we define something called Bellman operator here, which is essentially an operator that takes a value function and computes r plus gamma times this expectation. So here t pi of q pi is this value. We can also define some other operator which is called Bellman optimality operator, which is defined this way, that for a value function q, when we apply this Bellman optimality operator t pi, it computes a function which, when we evaluate it at state x and action a, would be equal to r of x and a plus gamma times p of the x prime condition x and a times maximum of q at the next state x prime and a prime, and maximum is our actions a primes. So this is called Bellman optimality operator. Why is it interesting? The reason it is interesting is that we have these two important equations here. The first one you have already seen, it's Bellman equation. So we say that q pi is equal to t pi q pi. And for the Bellman optimality operator, we also have this property that Bellman, the optimal value function q star, is equal to t star applied to q star. And one important property of them is that these equations are, the solution to these equations are unique. So if you find a q that satisfies this equation, that would be q pi. And if you find a q that satisfies this equation, that would be q star. So, okay, so let's go back to value-based methods. So these are Bellman equation, are important properties of the MDP. Value-based methods try to find the q hats such that they approximately satisfy this Bellman equation. I mean, if you satisfy it exactly, that would be great. That would be our, say, Q star. And if we find it approximately, that's still good enough, because then hopefully we can use it in order to find a good enough policy. And how do we do it? We do it using this gridification step, which is, or using greedy policy, which is essentially given some Q hat, we find the action for each state that maximizes that Q hat. And if Q hat is close to Q star, then the value of this policy, so Q of greedy policy of Q hat, is approximately close to the optimal action value function or optimal value function. Okay, so this is the basic of value function or MDPs. And now I'm going to talk about some methods for finding okay, so I talked about the basics of MDP and important properties of it. Now let's talk about how we can find the optimal value function. And I'm going to talk about two important classes of methods. One is called value iteration and the other is called policy iteration. These are the basis of many reinforcement learning methods. So let's talk about first value iteration. So value iteration is very simple. It basically says that we should repeatedly apply the Bellman operator, T star, to our current estimate of value function. So this is defined by this kind of operator, or this iteration that for QK, we apply Q star to get QK plus 1 and do it again and again. So visually, we can see it like this, that if the x-axis, horizontal axis, is the state space, or state action space here, actually. So I show it in one dimension, but just depending on this dimension of state space, it can be much higher dimension. But here for visualization purposes, I just show it by one-dimensional horizon, or horizontal axis, and the y-axis is the magnitude of that function. So if we have this QK, this is one function, the current estimate of the action value function. We apply T star to get QK plus 1, this kind of sine color curve. And then if we do it many, many different times, we gradually converge to optimal value function. The reason that we converge is due to the contraction property of the Bellman operator. So what is the contraction property? The contraction property of the Bellman operator essentially says that if you give me two value functions, Q1 and Q2, say these points, Q.1, Q1, and Q2, and I'm here is kind of like this space of value functions. And if suppose they have the distance of 1, according to some measure, or distance measure, and then we apply this Bellman operator to them. So we get T star of Q1 and T star of Q2. Their distance would decrease, and it would be at most gamma if we start from distance 1. Or in the equation, this is the same as the first term, minus T star Q0, T star Q star. T star Q star, so this is, you see that we have T star applying to once to Q0, once to Q star. Because of contraction property, we have this becomes smaller than gamma times Q0 minus Q star. So you see that after applying T star to Q0, the distance becomes a bit smaller. So for value iteration, after K or K plus 1 iterations of it, we have Q of K plus 1, which is here. And we want to compare the distance with Q star. We can write it the K times application of T star to this Q0 minus T star of Q0. So again, T star Q0 comes from being equal to Q star because of the Bellman equation. And if we do this, basically at each step, I can take one T star out and get one gamma out of it. So doing this exactly like the first line of equations that I have here, I get gamma to the power of K times Q star minus, times norm of Q0 minus Q star in infinity norm, the supremum norm. And you see that because gamma is smaller than 1, when K goes to infinity, the right-hand side converges to 0, showing that the difference between Q star and QK gradually goes to 0. So this shows that QK converges to Q star. Okay, so this is the basic idea of why value iteration converges, but we have some challenges, of course. One is that if the problem has a large state space, so for example, X is not finite, but is a subset of Euclidean or d-dimensional Euclidean space, Rd, and say D is some number like 5, 10, or something like that. And this happens in many real-world applications. For example, if you have a robot, the state of the robot is usually described by a real-valued vector. Part of the state might be the image that comes through the camera, and that's already thousands of dimensions. So what is the problem with large state space? One problem is that exact representation of the value function becomes infeasible in most cases, because to represent it exactly, we need to represent this function Q of X and A for all possible X and A's. But when the state space is large, like subset of real, or it's R to the power of D or subset of it, we have infinite number of states. So that's very large, and we can't represent it on computers. The other is that if you recall the Bellman operator, it was defined by this integral, or this expectation. You see that this is an integral over the state space, so over d of x prime. And this integral, when the state space is large, becomes very difficult to solve. So this is computationally challenging or impossible to do it exactly. So this is one challenge. Like when the state space is large, doing value iteration exactly is challenging. The other issue is that when the dynamics is not known. So if we don't know P, we can't really apply the value iteration exactly, or at all. So, and this is the case in reinforcement learning. In reinforcement learning, we often don't know the dynamics. We just have an agent that is interacting in the environments, and it collects some data, samples, but we don't know the dynamics. So maybe as a kind of side note, this is interesting because this is one of the differences, main differences between, say, optimal control and what people do in reinforcement learning. That in reinforcement learning, we usually don't know the dynamics, and our optimal control, we often assume that the dynamics is known. Of course, we have adaptive control, and we can have adaptive dynamic control, adaptive optimal control. And in that case, yes, we may not know the dynamics anymore, but often, at least in control, we assume that we know the structure of the dynamics. So for example, we know it's a linear dynamical system, we just don't know the parameters of it. So the adaptive control procedure tries to, say, identifies the dynamics in some of the approaches, like say indirect self-tuning regulation. Okay, anyway. Okay, the question is that whether there is any hope when the state space is large. As I explained, when the state space is large, we cannot really represent the value function exactly. The integral is, in the definition of the Bellman operator, is difficult or impossible to calculate, and we don't even have the model. So what can we do? So here comes two important ideas. One is the approximate dynamic programming, and the other is batch reinforcement learning. So approximate dynamic programming is essentially the idea that maybe we, instead of doing dynamic programming, like doing, say, value iteration, which is dynamic programming method, we do it approximately. And the batch reinforcement learning is that instead of having the model, maybe we have only data coming from the model. And in batch reinforcement learning specifically, we assume that we have an agent that has collected data, the data for us, and we are given that data, but we are not, the agent is not able to interact with the environment anymore. So what we have in batch reinforcement learning is kind of tuples in this form, like n tuples in the form of xi, ai, ri, and xi prime. So here you see, say, x1, and we choose action A1. I'm not showing you that action here. And we get at the next state, we get to x1 prime. So red points are next states. Distribution of next states, xi primes, comes from P, the distribution P, which is conditional on xi and ai. And the same for the reward. So here essentially we have these data points that comes from interacting with the environment. They have already been collected, so that's what. So we have a batch of data and data point, which they tell something about the dynamics without actually knowing the dynamics. And as we will see, this might actually be enough. So here what I showed you, maybe just mention here that here what I showed you here was kind of a bunch of initial xi's, x1, x2, x3, and so on, are kind of randomly sampled in the environment, maybe independently from each other. But in many cases, we also have follow a trajectory. The agent follows a trajectory. So we start from x1, we go to x2, which x2 becomes x1 prime. From x2, the agent goes to x3, which x3 is also x2 prime, and so on. So in this case, we have a single trajectory, and the data points are dependent. Here, the samples are independent. So this doesn't matter much in the description of algorithms that I'm going to talk about, but it changes the way that we analyze these algorithms. Okay, let's talk about the approximate version of value iteration. So it's approximate value iteration, or AVI, and this is the basis of many modern reinforcement learning algorithms, such as deep Q network and its variants. Okay, so what is the idea here? Recall that when I was talking about value iteration, I showed you this kind of graph that we have a QK, we apply T star to get QK plus 1. And the idea was that if you do it many, many times, asymptotically it converges to Q star. Now we cannot apply the Bellman operator exactly. What we can do instead is do it approximately. How? Let's see it a little bit more closely. So here, again, the horizontal axis is the state action space. We don't, what we have is that a bunch of data points from a bunch of states, essentially, like xi's that we have, or xi ai's. So here I show them with these red dots, or the x-axis of these red dots correspond to xi's, essentially, xi or ai's. And what about the y-axis? The y-axis, you see that each of these points are kind of around this T star of QK, this green curve, but not exactly. So what are those red curves or red dots? they are defined this way. For ith point, we define them as their value would be Ri, reward I, plus gamma times maximum of our A prime of Qk evaluated at xi prime and A prime. So if you give me Qk and also a tuple xi, ai, ri, and xi prime, I can compute this quantity. And this quantity essentially shows the y-axis in this graph. So this is interesting because if you look at this figure, it seems that these points are kind of close to this red curve, or sorry, the green curve, T star Qk, and it seems that they are like noisy version of it. And in fact, we can show that if they are noisy version of them. So if we take the conditional expectation of this quantity, Ri plus gamma times max of Qk, so here I show you without the kind of index of I. So I showed R plus gamma times max of Q evaluated xi prime. So the conditional expectation of it, conditional starting from state X and action A, is exactly the same as T star Q being evaluated at X and A. So what does it mean? This means that these points are essentially noisy versions of T star Qk. We don't know T star Qk for all the possible states, but we know them, or we have the noisy version of them at certain number of states corresponding to these red dots. So this is interesting because the problem of finding finding a function given noisy samples from it is the problem of regression. So problem of regression can be formally defined as having some random variable. We want to find the conditional expectation of it. We see that the conditional expectation of it is exactly the Bellman operator applied to T star Q. Now recall that this is what we actually want to compute. Like here in the left-hand side, we want to compute given Qk, we want to compute Qk plus 1, which is T star Q. Okay, we can't compute it exactly, but from here we have the noisy versions of it. So this is interesting because this converts the problem of computing the Bellman operator to, which is kind of dynamic programming problem, to a problem of regression. And problem of regression, of course, we know there are many different methods to solve regression problem. So one of the examples or one of the methods is based on solving this kind of empirical risk minimization. So what is this showing here? We are saying that in order to find Qk plus 1, let's solve this optimization problem. This optimization problem is saying that find a Q in some function space that minimizes this error term. So what is the error term? This is summation over all data points of the squared error between Q evaluated at XIAI minus this thing that I show or denote by T hat of star, which is exactly this quantity here. So I just use a more compact form. Applied to Qk. So we know Qk, we know XIAI, so we can compute this quantity. This is called empirical Bellman operator. And then find a Q that when evaluated at XIAI, the distance of it is minimized in average over data points. And the distance here is a squared error. So this is known, this is an approximate value iteration, also known as fitted value iteration or fitted Q iteration. It's called fitted because we are somehow fitting a function to these data points. And this is the basis of many methods. One important question here, maybe I should go back here and emphasize, show this function space F explicitly. One important question is that how should we choose this function space? Or how should we choose the function space where this Q belongs? There are many different choices. So for example, we can choose a linear functional space with features phi. So essentially that function space would be written with a set of functions, Q functions, that are in the form of phi transpose X and A times some W. So phi is given, it's basis functions or features, but multiplied by W, so this is a vector. And the vector is unknown, so essential space. But we can choose also other ways to represent this function space. For example, we can use decision trees, or a bunch of decision trees, or randomized trees. We can also use something like reproducing kernel Hilbert space, which is the same kind of kernel space that people, when they talk about support vector machine, they're talking about. We can also use a function space that is represented with one particular neural network or deep neural network. These are all valid choice of function space. Okay, one important question now is that how we should choose the function space. So just notice that we had this function space and we could possibly choose it to be different types of function spaces. What is the right way to think about the choice of this function space? One way to think about it is very similar to what we do in supervised learning in terms of approximation error and estimation error, or bias and variance. So let me describe it very briefly. So the idea here is that we have this kind of function space I'm showing you with an orange ball, and the size of this orange ball shows how large the function space is. If it is larger, I show it with a larger ball here. So what happens is that at each iteration of, say, approximate value iteration, we start from some function, qk. We apply the Bellman operator, t star, to get to t star qk. So this t star qk may not be within this function space anymore. Maybe we cannot represent it within this function, with any function within this function space. So what is the result? The result is that we have some approximation error, which is basically the error or the distance between this function, t star qk, and closest function from this function space, capital F. So that would be the function approximation. There's also other ways to represent this function space. For example, we can use decision trees, or a bunch of decision trees, or randomized trees. We can also use something like reproducing kernel Hilbert space, which is the same kind of kernel space that people, when they talk about support vector machine, they're talking about. We can also use a function space that is represented with one particular neural network or deep neural network. These are all valid choice of function space. Okay, one important question now is that how we should choose the function space. So just notice that we had this function space and we could possibly choose it to be different types of function spaces. What is the right way to think about the choice of this function space? One way to think about it is very similar to what we do in supervised learning in terms of approximation error and estimation error, or bias and variance. So let me describe it very briefly. So the idea here is that we have this kind of function space I'm showing you with an orange ball, and the size of this orange ball shows how large the function space is. If it is larger, I show it with a larger ball here. So what happens is that at each iteration of, say, approximate value iteration, we start from some function, qk. We apply the Bellman operator, t star, to get to t star qk. So this t star qk may not be within this function space anymore. Maybe we cannot represent it within this function, with any function within this function space. So what is the result? The result is that we have some approximation error, which is basically the error or the distance between this function, t star qk, and closest function from this function space, capital F. So that would be the function approximation error or approximation error. We have another source of error too. The other source of error is because, which is called estimation error, is because we use a finite number of data points in order to estimate the best function in that function space. So I go a few slides back. So here, remember that we use n number of data points. N might be fine. N is finite. It's like 1,000, 10,000, million, or even a billion, but it is finite. So when we do this minimization, we have some kind of error that comes from finiteness of the number of points used in that minimization. So that is causing an estimation error. So it seems clear that if the function space is larger, I'm showing you kind of larger function space, the approximation error gradually decreases or might be even 0. But on the other hand, the estimation error depends on the size of the function space, and it is larger when the function space is larger. So here, when the function space is small, we have relatively large approximation error, but the estimation error is small. When here function space is too large, we have no approximation error, but the estimation error would be large. This is the case of an overfitting, and this is the case of underfitting that people usually talk about in supervised learning. So we have similar phenomenon happening in reinforcement learning to this batch setting. And of course, this is more general than the batch setting, but here it is very clear. And if the function space has the right size, we basically have the right trade-off between the approximation error and estimation error, and the total error would be minimized. So how can we choose the right size for the function space? One idea is to use regularization. So what's the basic idea? The basic idea is that we should start from some very large function space, maybe large function space that can represent any continuous function. So that's a very, very large function space. But then control its complexity using regularization. So don't actually use the whole function space, but with some regularization, focus only on a subset of it. So if you want to implement this idea in fitted Q iteration or approximate value iteration, the idea is simple. We just add a regularization term here. So recall that this was the optimization problem that we solved. We had the squared error, but we add some regularization term that essentially gives a preference to functions that are somehow simpler in some sense. And one way to think about this is that we choose a very large function space to be, say, reproducing kernel Hilbert space with a kernel that is universal, so it can represent any, say, continuous function arbitrarily well, and then use the norm of that function, that Hilbert space. So here is the norm of Hilbert space squared as the regularizer. So this is called regularized fitted Q iteration algorithm with reproducing kernel Hilbert space. Of course, we can use other function spaces and use similar ideas, similar regularization. Okay, so far I talked about approximate value iteration as the approximate version of value iteration. So that essentially helps us solve function problems with large state space. And when we don't have the model exactly, but we only have data. We can also use the idea of policy iteration in order to solve MDPs, and then use the approximate version of it, API, in order to solve problem with large state space. So let's just recall what policy iteration is. Policy iteration is this procedure, this iterative procedure that involves two steps: policy evaluation and policy improvement. So what is policy evaluation? Policy evaluation is essentially this sub-problem that given one policy, you find the value function for that policy. So suppose I give pi to this policy evaluation. It tries to solve this Bellman equation, T pi, Q pi equal to Q pi. And remember, if we have this relation, that function that we find here is the unique value function for that policy. So the output of that policy evaluation is the value function Q pi. And then we go through the policy improvement step, which is basically is a module that gives a new policy that is better than the previous policy. And it is doing it, it's a very simple procedure. It basically finds the greedy policy. And recall that the greedy policy is defined like this. So the greedy policy for Q pi is the policy that at each state chooses the action that has highest action value function. So let's talk a little bit about policy evaluation, because that's a part that is actually requires some attention we want when we go to larger state spaces. So recall that if you find a Q such that T pi Q is equal to Q, then Q would be the value function, action value function for that policy, Q pi. So that's unique. So you assume that P, the transition kernel or transition matrix, and reward are known. So how can we solve this equation, or this Bellman equation? One is that, notice that this Bellman equation for a fixed policy is essentially a linear system of equations. So we are solving the linear system of equations that is essentially saying that for all x's and all i's, q of xi is equal to reward at that state and action plus gamma times summation over all x primes of p of x prime condition of x and a times q of x prime and pi of x prime. So you see that, notice that it's a linear system of equation. Your left-hand side is linear, it's q, linear in q. And here's reward plus gamma times linear summation of other q's. So if we know Q, P, and R, we can solve this. So this is one approach. This is the other approach is that using something like value iteration, which basically does this computation that at each iteration applies T of pi to QK to get QK plus 1 and repeats this many, many times. So recall that this is a slightly different from value iteration I talked earlier. So, previously, we had T star, the Bellman optimality operator. Here we have T pi. So this is value iteration for computation of the Q pi. And very similar to before, T pi is a contraction. Previously, we had T star is in contraction, but here's T pi is contraction too. And as a result, we can get that Q of K is converging to Q pi. So this is one approach, another approach. And then another approach is doing something called Bellman error minimization. So here the idea is that find a Q such that the difference between the norm of the difference between Q and T pi Q is minimized. And so why this works is that if the norm is 0, so if there is no difference between them, say if the norm is 0, then Q minus T pi Q should be 0, which basically means that Q minus T pi is equal to T pi Q. which, if you recall from the Bellman equation, then that basically says that this is a solution of the Bellman equation. So, which is the q pi. So if we solve it exactly, like this, the norm becomes 0, then it gives us q pi. If there is some error, then it is approximately q pi. So the other step of policy iteration is policy improvement. So here the idea can be stated by this proposition. Proposition says that suppose that the improved policy pi prime is the greedy policy with respect to q pi. So what does it mean? It means that t of pi prime of q pi is equal to t star of q pi. So if we choose the pi prime to be the greedy policy, it satisfies this relationship. Because recall that t star has a max in it, and if we choose pi prime to have to be the greedy policy, it is as if we are using the maximizing action. So maybe you need to think a little bit more about it, why this is actually true, but that's the property of the greedy policy. So if we choose pi prime to be the greedy policy, we have one important property. And what is the important property? The important property is that q of pi prime, so the value function or action value function of this greedy policy, is not smaller, it's equal or larger than q pi. So it says that the value of the new policy that we get is at least as good as the previous policy, and it might actually be better. So this is interesting because it says that if we do policy improvement, we are getting a policy that is possibly better than the previous policy. And now, so here the idea is that we get first evaluate the policy q pi, we improve it, so we get pi prime, and this pi prime is a better policy. We compute is q, because we don't know, we just find a better policy. By doing policy evaluation, we find the value of it, so it would be a q of pi prime, do policy improvement, and then we get another policy that is again better. And if we do it many, many times, it can be shown that it converges to the optimal policy. And usually we have this property that this convergence can be actually relatively fast. At least in practice, it might be just a few steps of policy iteration would be enough to find the optimal policy. And I think in theory, there are results that it's not as fast, but it is still polynomial in the size of state space. So here again, we have similar challenges as before. The challenge is that if the state space is large, we can represent the value function, or computation of the integral in the Bellman operator would become very challenging. And also the other challenge is that in RL, the dynamics is not known. So even if we can represent things exactly, we don't know that P matrix or P kernel. So here the idea is that we do this policy iteration approximately, and the basic thing that should change is the policy evaluation module, which becomes approximate policy evaluation, which essentially says that instead of finding q pi, we find the q hat pi, the output of this module, which is approximately equal to q pi. And hopefully, if the approximation is not too bad, we still get kind of reasonable result, and this whole approximate policy iteration would still work. So in approximate policy iteration, we move from solving the Bellman equation q pi being equal to t pi q pi exactly, we move from solving this exactly to solving it approximately. So if we find a q hat, which is approximately equal to t pi of q pi. And okay, so let's try to see how we can do it when we have some batch of data. So because as in the case of approximate value iteration, we have these data points of xi, ai, ri, xi prime, and xi prime comes from the transition kernel, p, the probability of going to another state condition xi and ai, and the same for the reward. So these data points are given, but we don't know p. Recall that recipe for exact policy evaluation was either solving linear system of equation, doing value iteration, or Bellman error minimization. When the size of the state space is large and we don't have the model, solving the linear system of equation becomes infeasible or very difficult. So if the size is very large, we can't, this linear system of equation becomes, say, becomes very large. So say, assume that state spaces RD, so this has infinite number of states. So we can't really solve it. And also when we don't know P, we can't even form this linear system of equation. So this leaves us one possibility of doing value iteration. So here, instead of trying to solve this exactly, we say that we solve it approximately. So we find a Q such that T pi of Q is approximately equal to Q, and then hopefully, and it can be shown that this is the case, that Q will be approximately equal to Q pi if we solve this Bellman equation approximately. So here we can solve these two value iteration approximately. If we have the model, but the state space is very large, or if we don't have the model, but we have data, we can still do the approximate value iteration, similar to what I explained before. We can also try to solve this Bellman error minimization, which basically says that try to solve this optimization problem. But here notice that we can use, instead of using an exact representation of Q, we might be able to use a function approximation for it. So maybe we can't exactly represent that Q, but we use a function approximation for it, and still solving this optimization problem is meaningful. Another option is doing something that's called least squares temporal difference, or LSTD methods. And I'm going to talk about it later. Okay, so let's talk about Bellman residual or Bellman error minimization. So here we assume that we represent the value function within the function space F, capital F. For example, if that value function space is a linear function space of linear functions, which by that I mean that Q is represented this way. Q represented as Q of X and A is equal to phi transpose of X and A and W. So phi would be the features or the basis, and W would be the parameter that parameterizes the function space, the function in the function space. So this is one way. And here I'm showing that linear function space with this kind of plane or hyperplane. So Q1 is a function on this plane, and it can be represented, of course, exactly. Now suppose I apply T pi to that Q. The result might be a function that is outside that function space. So it gets to this point, which is outside that function space. So the Bellman residual would be the difference between this Q and T pi Q. And the goal here in Bellman error minimization is to find a Q that minimizes this distance. So notice that for different choice of Qs, we have different distances. So maybe Q3 has a larger distance or has a larger Bellman residual, and Q2 has a smaller Bellman residual compared to the Bellman residual of Q1. So when we solve the minimization problem, that we have here, like solve this minimization, we are essentially trying to find the Bellman Q function that has the smallest Bellman error. So one question, of course, is that what is the relation between having a small Bellman error and the quality of that value function? So suppose I find the Q hat that has a small norm of Q hat minus T pi Q hat. Does it entail that the difference between the real Q pi, so I'm showing that with this green star, and Q hat is also small or not? So here the idea is that, yes, we can show that this is indeed the case, and this is shown with this upper bound that says that the difference between Q pi and Q hat in the supremum norm is smaller than some constant multiplied by T pi Q hat minus Q hat in the supremum norm. And the constant is 1 divided by 1 minus gamma, the discount factor. So say if the discount factor is 0.9, this would be 10. So if we ensure that the distance, the Bellman error is smaller than, say, 1, then the difference between Q hat and Q pi is going to be smaller than 10. And if we find a function Q hat that has a very, very small error, like 10 to the power of minus, say, 3, then we can guarantee that Q pi and Q hat are also small. So this can be shown here. I go through the proof quickly. So suppose we have, I essentially write the left-hand side, Q pi minus Q hat is equal to T pi Q hat. So why? Because of the Bellman equation. So Q pi is equal to T pi Q pi. And then I add and subtract T pi Q hat minus T pi Q hat plus T pi Q hat. So you see that these two terms go away, but they're the same essentially. Minus Q hat, which is that last term on the left-hand side. Now, notice that this Bellman operator is a kind of fine operator. And after simply kind of getting rid of the reward term, which is the same, so we get here from these two first two terms, we get gamma times P pi of Q pi minus Q hat plus T pi Q hat minus Q hat. So notice that this Q pi minus Q hat is the same term that we have on the left-hand side, with the difference that it is multiplied by this matrix gamma times P pi. I mean, here we can think of it as a matrix, but in general it's kind of linear operator, but that doesn't matter. So we reorder these terms to get that one identity matrix minus gamma P pi times Q pi minus Q hat is equal to these two terms, T pi Q hat minus Q hat. And then we take the inverse of this I minus gamma P pi to get that Q pi minus Q hat is equal to inverse of I minus gamma P pi times T pi Q hat minus Q hat. And I mean, we need to kind of show that actually we can take that inverse, but that's not too difficult. This matrix is invertible, so basically we can show that. And also we can, there are some properties about the norm of these matrices, and especially this stochastic matrix P pi. So P pi is a stochastic matrix, so its supremum norm is smaller than, is equal to 1 actually. So if we take supremum norm of both sides and doing some kind of standard linear algebraic manipulations, we get that the supremum norm of Q pi minus Q hat is smaller than 1 minus gamma, and this 1 divided by 1 minus gamma comes from inverse of this matrix, or the norm of this matrix, times the norm of this vector, which is T pi Q hat minus Q hat. So you see that we prove this relationship. So this is, just again, I repeat it, this is reassuring because it shows that if we can do Bellman error minimization, the result provides an upper bound on the quantity that we actually care. So we find a Q hat that is close to Q pi if we have a small Bellman error. So the procedure would be like this. So we define the loss, that is Bellman residual minimization loss, to be the difference between Q minus T pi Q. Here I'm using some form of L2 loss norm instead of supremum norm that we had in the previous slide. So there are reasons for doing that, but that doesn't matter right now. So, and then we choose a function space, maybe linear function space or neural network or decision trees, and then we try to find the Q hats. So we do this. Here the problem, of course, is that if we only have access to data points, so we cannot compute T pi Q exactly. But we can do something like the empirical version of it. So we can use empirical Bellman error or empirical Bellman operator and define this empirical Bellman residual minimization loss, which is defined as summation over n data points of Q of xi ai minus reward of ri plus gamma Q of xi prime and pi of xi prime. So this is a well-defined loss function, and we can try to minimize it. And the hope is that if we can find a good minimizer for this loss function, then the Q hat that we find is going to be a good approximation of Q pi. There's unfortunately a small catch. The catch is that one can show that this empirical loss is not biased. So it is not unbiased, it is biased. So if we take expectation of this norm, so recall that dn, I'm defining it here. dn is basically emphasizes that or denotes that this is an empirical loss. So there's a summation. So if we do this computation, compute the expectation, we get that the expectation is Q minus T pi Q. So this is the Bellman residual error, Bellman error that we have here. So this is exactly this term that you ideally want to minimize, plus some other extra term, which is T pi Q expectation of squared error between T pi Q and T hat pi Q. So this term is in general not zero, which basically means that the loss that we are trying to minimize would not, in expectation, would not be the same as the loss that we really want to minimize. So the problem here is that this extra, so this is kind of bad because it means that the optimization that we want to solve, we cannot really solve it directly. And if we kind of think a little bit harder about this, we see that this extra bias term, like this term, depends on the value function. So different choice of value function leads to different values of this extra term. This is different from the supervised learning when the extra bias is independent of this, your estimate or your estimate. In that case, if you have that extra term, that's okay because it doesn't change the solution of the optimization problem. But here, this extra term changes the solution of the optimization problem. So notice that if the dynamics is deterministic, this extra term, which is T pi of Q minus T hat pi of Q, and remember that T hat pi is this term, is R plus gamma Q of xi prime. So if xi prime is a deterministic function of xi and ai, so there's no randomness in it. If you give me one xi and ai, the results for deterministic system would be always the same xi prime. In that case, T hat of pi of Q would be exactly the same as T pi Q, and this term would be 0. But if the dynamics is stochastic, which is in many cases, it is the case in many RL problem, then we have this extra term. If it is deterministic, then that's okay, and we shouldn't be worried about it. And this is related to also double sampling issue in reinforcement learning, that if you take a look at, say, standard RL textbook, you see that it's talking about double sampling issue. So this is essentially the same. So another idea is to do the policy evaluation when we have a large function space, is doing something called least squares temporal difference. So the original formulation of it can be described this way. Just pay attention to this function space, or how this Q is changing in this function space or moving around. Suppose we start from Q. Okay, so this kind of plane is again the function space. So we can only represent Qs within that function space. We have this Q. We apply the Bellman operator. We get T pi Q. T pi Q may not be represented or cannot be represented in this function space. So we project it back to that function space. So this capital pi is the projection operator, and capital pi T pi Q would be this process of taking Q, applying Bellman operator to it and projecting back. So capital pi T pi is the projected Bellman operator. LSTD basically, in the original formulation of it, tries to find a fixed point of this projected Bellman operator. So essentially tries to find this equation. So it finds a Q such that Q being equal to capital pi projection, the Bellman operator Q. So this also can be formulated. Okay, so notice that the Bellman, the projection can be also written as this optimization problem. So capital pi of Q can be written as the solution of this optimization problem. So there should be equality here. So this is argmean of some function h that tries to, h belongs to that function space f, and tries to find the h that is as close as possible to Q. So Q here, of course, is a function that is outside that function space. So we find the L2 projection of that function space, of that function onto our function space. So here, one question, of course, is that whether we can always solve this equation or not. We can solve this equation if capital pi T pi is a contraction operator. So recall that contraction operator is the operator that makes the distances between functions after being applied to them smaller. So Bellman operator is a contraction, but projected Bellman operator is not a necessary contraction. Unless this capital pi is defined with respect to a norm that comes from the station distribution of the policy pi. So I didn't go into this detail very much, but if we define this minimization according to some norm that is defined based on station distribution of a policy pi, then that operator is a contraction. But that doesn't matter. I mean, maybe it doesn't always have a fixed point, but we can always formulate it as an optimization problem. So we can instead find a minimizer of Q minus capital pi T pi of Q. And this optimization problem is always well defined. And in case that this nu, the distribution that defines the projection, is a station distribution of pi, then the solution of this optimization problem is the same as the fixed point solution. So why I'm going through this, the original formulation of LSTD didn't talk about this optimization-based viewpoint, but it turns out to be helpful. The reason it's helpful is that now we can try to solve the problem of finding a good Q as this optimization problem. And this works even when the data point is not coming from station distribution of that policy. So it allows us to use a batch that is generated from another policy and still use that batch of data in order to find a policy or value function for another policy. So, okay, so we have this optimization problem, and we can also equivalent write this optimization problem as these two coupled optimization problem. So what are these two coupled optimization problem? One is solves this H1 that gets as input Q, a function Q, and tries to find some function H or H prime here that minimizes the distance between H prime and T pi Q. So given Q, we apply the Bellman operator to it. It gets here from Q here, it gets to this point, and H prime is essentially this projection point. And then the other step is Q, I'm showing by QLSTD, is the minimizer over some functions Q of the distance between Q and H of Q. So H of Q was this point, this is Q, so this second optimization problem tries to minimize this distance. And the first optimization tries to find this distance. So essentially the first one is trying to do projection, the second one is trying to solve the, minimize the difference between Q and the projected value of T pi of Q. So these optimization problems are equivalent to this optimization problem at the top of the page. And also we can write the empirical version of it. So empirical version of it would be these two coupled optimization that essentially we replace integrals that are using the definition of norms with the summation. So for H hat, we have summation over n of squared error between H of xi ai minus reward I plus gamma q of xi and pi of xi prime. And then for q, it would be similar. It would be the minimum of q of xi ai minus h hat of xi ai and q. So notice that these two optimization problems are coupled, right? Because h here is a function of q, and q is a function of h. So when we change q, h, the minimizer, h hat also changes. So in general, that might be a difficult optimization problem, but we can show that for some class of function spaces, we can find a closed form solution. Okay, now let's, we have again, as before, you recall that one issue is that how to choose the right function space in order to balance the approximation error and estimation error. And one way to think about it, or one way to deal with it, is that to start from very large function space, but then control its size or complexity or effective size, essentially, by adding some regularization term. So this gives us the idea of regularized LSTD, which is essentially adding these two regularization term here. So this one and this one to this optimization problem. And then chooses the function space to be very large function space. For example, it can be a reproducing kernel Hilbert space with a kernel that is universal. Okay, so this gives us the idea of regularized least squares policy iteration, which is essentially least square, approximate policy iteration algorithm that uses regularized LSTD for the policy evaluation step or approximate policy evaluation step. The policy improvement is easy because it's just stratification of the policy. Let's briefly talk about the theoretical analysis that we can provide for these batch reinforcement learning methods. We don't have enough time to go into any detail, But I think it might be useful to talk about first why theory works or why theory is important, and then give some very high-level idea what type of things we can say about batch reinforcement learning, what kind of theoretical thing. So there are many different reasons that we are interested in doing a theoretical analysis for these type of methods. One is that we want to show the soundness of algorithm. Basically, we want to know if the method works if we feed a lot of data points, or under what condition it would work. The other is that about the efficiency of the algorithm. Suppose it works if we give a lot of data, but how fast it can learn. Does it learn faster for some problems? Like, are there this class of simpler or more difficult problems or not? And also, I guess it might help us doing theoretical analysis think about how we can design newer and better algorithms that, for example, can learn faster. So this is the general reason that we do theoretical work, or at least some of the reasons. So in supervised learning, say in classification, regression, people have studied their learning algorithms and provided some kind of theoretical guarantees on why they work. This is relatively more recent for reinforcement learning. I mean, not completely recent, but much studies started in 2000s and after that, especially for the type of analysis that basically provides some kind of convergence guarantees for batch reinforcement learning algorithms. And these type of analyses are a bit different, but maybe we can divide them to two main steps. One is that statistical analysis of each step of, say, approximate value iteration or each step of approximate policy iteration. And the other is that error propagation type of analysis, which basically says that if you make some error at each step, how do those errors affect the final outcome? So recall that in value iteration, we had this nice contraction property, and because of that, we could get results like this, that qk minus q star after k iteration would be smaller than something in the order of gamma discount factor to the power of k. So in value iteration, everything is nice as long as gamma is smaller than 1, which is the case for discounted problem. But when we go to approximate value iteration, we are facing some challenges. One challenge is that, well, we can't do Bellman operator exactly, so we need to use data and solve an optimization problem. And because of that, as I explained, we have some kind of error. The error can be approximation error, part of it estimation error. So we do each step of either value iteration, applying the Bellman operator approximately. And the same can be said about the policy, approximate policy iteration. Each step of policy evaluation there has some kind of error. So as a result, one step of this kind of analysis is that to study how these errors are propagating through this process. Like if we make some error at step 1, step 2, step 3, how do they accumulate and affect the quality of the final value function that we find, or the quality of the final policy that we find. So one way of doing it is basically simply saying that how much error we have in approximation. So we can define something like epsilon k to be the difference between t pi qk minus qk plus 1. So if qk plus 1 is computed exactly, so be equal to t pi qk, this error would be 0. But if it is not, we have some error, which might be because of approximation or error or estimation error, this would be non-zero. And then we can study the effect of these errors and provide a guarantee like this. That's saying that basically the qk, q capital K after capital K steps of doing this approximate value iteration, the difference between the true value function and what we find is a function of summation of terms like this, that summation over k, small k from 0 to capital K minus 1 of gamma to the power of capital K minus 1 minus K of the norm of those errors at each step, plus some gamma to the power of K of the difference between the initial point, initial value function that we started and the true one. So you see that this second point, the term is not of much a concern, because if this is finite, then gamma to the power of capital K would be small number. But then this other term is important and showing that if we make some epsilon error, the norm of it appears. And maybe it's also interesting to note that not all iterations are the same, and earlier errors will be forgotten. So you see that for epsilon 0, say, the error in the first step, we have a multiplier of gamma to the power of capital K minus 1. So it is kind of, the effect of it would be diminished. So this is the error propagation type of analysis. We also need to study like what is the size of this epsilon K's actually. So this is like a regression error, with the difference that the setting has some differences with the usual regression problem. So some of the differences is that, well, in regression, the target is always fixed. In, say, approximate value iteration or in RL in general, the target is moving. The objective function sometimes is not standard. So it is, for example, in approximate policy iteration, when we have policy evaluation using LSTD or Bellman residual minimization, the loss wasn't the usual regression loss that we have. One other source of complication is that we have dependent data. In many cases, data is not IID anymore. And then we have issues related to, say, off-policy, having off-policy data or distribution mismatch. It basically means that the data comes from a policy, say policy 1, but we are evaluating according to policy. We want to evaluate or find the QPI for policy, another policy. So despite all these things, we can still obtain kind of fast convergence rates for this statistical analysis. And we can show something like this. So for example, for regularized LSTD under some kind of conditions, we can show that the difference between the Bellman error of Q hat minus T pi Q hat squared would behave in the form of order of n, number of data points to the power of minus 1 divided by 1 plus alpha. And alpha is a parameter that describes how difficult or how complex the function space is. So basically this shows that if you have more data points, the error goes to 0 and the rate depends on the complexity factor alpha. So, and it turns out, I'm not going to detail, but this is the rate that we can get for regression with a similar type of assumption. So this rate is actually fast, and we can show that for regularized LSTD, we have optimal rate for policy evaluation. Okay, so just to conclude, here I started from basic MDP, talked about value iteration, policy iteration, and then talked about how value iteration, when we have large state space and when we don't know the model, can be extended to approximate value iteration, and the same for policy iteration. For policy iteration, for approximate policy iteration, I talked about two ways of doing policy evaluation. One was Bellman residual minimization, the other was LSTD. And I briefly talked about theoretical analysis and talked about error propagation, what it means, and also the statistical part of it. So what hasn't been covered? I mean, many things. There are many other ideas in dynamic programming that can be used and has been used, and I haven't talked about. For example, modified policy iteration, which is something between value iteration and policy iteration. The other is that, so for example, here, I didn't really talk about the function approximation was used to represent the value function, but we can also use function approximation to represent the policy. And the result would be something like classification-based approximate policy iteration, as well as something like actor critic type of algorithm, which is something between policy search method, direct policy search method, and value-based methods. I haven't talked about how we should choose function approximation class. How can we do feature generation? What are the non-parametric methods? I briefly didn't mention them explicitly, but those reproducing kernel Hilbert space-based methods can be seen as non-parametric approaches. And of course, in deep reinforcement learning, we use deep neural network, and this brings a lot of interesting question of like how to analyze a deep RL algorithm. And here there are concerns like computational concerns, which I didn't talk about at all, like how easy or difficult it is to solve those optimization problems, and whether we can convert those methods from batch setting to online methods that can kind of process each data point as they arrive. So instead of having collection of data points, we do processing estimation of the value function online. And another important question that I haven't answered or haven't talked about was basically how we should choose data efficiently. So here I assume that data has been collected and is given to us, but I haven't talked about what is a good way to obtain that data. And this is of course related to exploration, exploitation issue in reinforcement learning, but in a batch setting it's a bit different too. Okay, I think that's all. So there are some, in the slides we have some general references for topics that I talked about, and I think that's it. Okay, I hope you learned something from this lecture, and yeah, have a good day.
Thank you, Amir-massoud, for a very profound talk. It was very informative. So here we have some questions, and I would like to thank you for answering them during your presentation. So we can start with the follow-up questions that still is here. Darian asked that, is there any evidence to support this idea that with a smaller gamma in each step we can get closer?
Okay, hello, hi. Can you see me?
Yes.
Okay, perfect. Yeah, so what kind of evidence you want? I mean, you can mathematically prove that gamma basically describes how much contraction you have at each step. So that is true, you can prove it. But also if you try it empirically, you get those results that with smaller gamma, you converge faster.
Okay, thank you. And here is another question that if h is closer to t, then it's good enough to be the next approximate q, right? And why must the distance between h and q get minimized? And some other theoretical things here.
So let me see. Okay, so let me see. So if h is closer to t, okay, just I clarify. I mean, t is an operator, is not a function, right? So you apply. Let me see if I can use these slides. Okay, so what is happening is that. Do you also see my cursor here?
No, unfortunately not yet.
Let's see. Maybe pointer.
Yes. Now it works.
Okay, so when you choose Q, let me just try to explain it briefly. When you choose Q for any Q in this function space, and then apply this operator, you get to this point, like T pi Q, which is outside your function space.
Mm-hmm.
So you cannot represent that. That's why this edge, which is the projection step, is trying to find a point in this function space that you can essentially represent. Like T pi Q, you cannot represent. H you can represent. You can represent. Now you have different choices of Q. Like there are many infinite number of Qs in this function space. Which one you should choose? Basically, this optimization framework of LSTD basically says that choose the one that after you choose Q and then kind of apply the Bellman operator, get to this T pi Q, and then project it back. So a point that you can now represent, the difference between these two things would be minimized. Or maybe I should just say something kind of related, is that in original formulation of LSTD, as I mentioned, it is formulated as a kind of fixed point operation or fixed point equation. So basically, what we have is that trying to, I think I have it here. So we try to find a Q that satisfies this fixed point equation, which is equivalent of formulating it as an optimization problem. This slide's gone. But,
okay.
Okay, it's back. Yeah. So I hope it kind of clarified a little bit.
Okay, thank you. And the next question is, how can we close this presentation? Okay, what is inverse reinforcement learning, and are there any differences between IRL and imitation learning?
Right. So, I mean, inverse reinforcement. So here in reinforcement learning, you have a reward and you want to find a policy that optimizes or maximizes some form of average reward, like discounted reward here in the talk, but there are also other forms. Inverse reinforcement learning is kind of like the opposite problem, that you observe some behavior, basically some set of states and actions, and then, but you don't know what reward has generated that or caused that. So you can think of it like this, that you have this agent that has some kind of reward and it solves some kind of, tries to find the optimal policy for that reward, and then executes that policy, and you only observe the actions, states and actions that it generated, but you don't observe the reward. So in inverse reinforcement learning, you are trying to now find the reward that caused that behavior to be generated by some agent that is trying to optimize it. So you want to basically figure out what reward the agent has been using. So I guess that's inverse reinforcement learning. And it is related to imitation learning. I mean, imitation learning is a kind of vast area. Some people might say inverse reinforcement learning part of imitation learning. Some people would say that no, imitation learning is something that is like this, that you see some states and action, and you want to essentially copy that behavior. You learn that behavior, but without necessarily finding the reward function that has generated that behavior or policy.
Okay, thank you very much. And the next question for convergence analysis, is it possible to use another norm instead of infinity norm?
Yes. So I think for infinity norm, I mean, there are two convergence analyses. I guess one part is the error propagation part. What I think usually it's done with supremum norm, but it also holds for, or similar results exist for LP norms, like L2 norm or other norms. For the statistical part, that we basically say we want to focus on policy evaluation, solving LSTD, and how if you have n number of samples, how accurate we get to the kind of the Q pi, say. For those results, we usually have results for LP norms, like L2 norms, and less for L infinity supremum norms, actually. So yes, in short, we can do it with other norms, and people have done it.
Okay, thank you. And the follow-up question is that using which method the LSTD optimization problem can be solved?
So the formulation that I mentioned, like two coupled optimization, if the functional space is a linear function space, or it's a reproducing kernel Hilbert space, which is again kind of linear in some sense, then we can have closed form solutions. So it would be the problem would be equivalent of solving some kind of matrix inversion problem. we can have closed form solution for it.
Thank you.
But in general, like if you have like original LSTD is formulated with linear function approximation, so there is always a closed form solution for it. But if you formulated the optimization framework and use, say, neural network for representing that, then it would be difficult. It would be kind of two-coupled optimization problem, and you may not necessarily find a global optimum, as usual is for deep neural network.
Thank you. And the next question is, it seems that we should calculate the last function resulting this approximation algorithm sequentially. Is there any way to do that in parallel?
Okay. I mean, there are. So in these methods, we need to go through a sequence of functions. Some aspects of that problem can be made parallel, but not these aspects of like applying the Bellman operator, at least in the type of method I talked about. So what people do to do it in more parallel form is that in the data collection parts, like there would be multiple agents collecting data at the same time and all of them updating the same function. So in that sense, it can be parallelized, but not in, say, the form of value iteration that you have to do things sequentially.
Okay, great. Thank you very much. And I think one more question probably is coming. Or multiple. But until these questions arrive, I have one question. Is there any library or any API that has this formulation implemented yet so that the developer can easily use them into their applications?
So, I mean, some of these, I mean, there are many libraries. Like OpenAI has some libraries. DeepMind has dopamine, I think. That's some of these methods or some of the RL algorithms have been implemented. I'm not sure if about LSTD or not. But yeah, I mean, for example, I talked about fitted value iteration, fitted Q iteration. DQN is one version of such an algorithm, and there are many libraries for that.
Thank you. So, if there are any questions, please write it down in the chat box. So we have another question. Is there any neurological or other biological studies for beta RL?
Okay, so what, I guess it depends on what you define by beta RL. Are you talking about like whether there are methods that people can get inspired from to design better reinforcement learning algorithms? I know there are people working on, I'm not a neuroscientist, so I'm not sure, but I know people working at the intersection of like computational RL as it is kind of practiced in machine learning, computer science, and those who work at kind of neuroscience or psychology. And I mean, there are a lot of connections, but I don't know if there is any kind of grand idea that people have found in neuroscience and brought it back to current RL method to make it better. But also I should say that, I mean, many of the current RL, or I mean, RL started in psychology, right? By work of Skinner's and others. And gradually people started to make them, those ideas more computational. So the framework that we have already today has been influenced by what have been done before in psychology.
Okay, thank you. And the next question is that how should we calculate policy or value iteration for multiple agents when they are affecting each other?
So there is this literature on multi-agent reinforcement learning. So essentially they can formulate, here things were formulated in Markov decision process, like there is a fixed environment and agent that is interacting with it. But you can also assume other agents, and then there is this thing called Markov game process. So I think for Markov game process, you can incorporate them, and there are some methods for doing that. Some of these methods are kind of similar, like equivalent of value iteration, but also the actions of other agents should be incorporated. So it is possible, but and people have done it since a while ago. If you search for it, you can find.
Okay, thank you. And the last question here is, can we incorporate model-based RL into batch RL for solving distributional shift issue existing in batch RL?
I guess, okay, I guess model-based RL is a hot topic. But also it is not a solved problem. I mean, if we learn a model that is good at this region of the environment, but we don't have any other samples from the other part of it, and then that model is not good, or it basically doesn't solve the distributional shift issue. So yes, I think we can incorporate model-based RL and batch RL, so I don't think there is an issue with that. But whether it completely solves distributional shift issue or issues like that, I don't think so, at least at the moment.
Okay, so thank you very much again for answering the question, and a very nice presentation. And I wish you a very wonderful Sunday in Toronto.
Thank you very much, and thanks for inviting me. I hope you enjoy the rest of the summer school. Bye.
Sure, bye. Okay, thank you everybody for attending this session. We had 3 nice talks, so I hope everyone has enjoyed these talks and learned many good things. Thank you very much again.